Well, hello everyone, welcome. For those who don't know me, my name's Yonik Seeley. I created Solr back in 2004 when I was working for CNET Networks, and CNET had the foresight to contribute it to the Apache Software Foundation. And then in 2007, I helped co-found Lucid Imagination to try to be the commercial voice for Lucene and Solr. So what I'm going to be talking about today are many of the changes that have happened since the Solr 1.4 release, which has actually been quite some time now. I'm going to be talking about things that are both in Solr 3.1, which was released just recently, maybe like a month and a half ago, and also development that's happened on Solr Trunk, which will be Solr 4.0 when it's finally released. And when that happens, who knows? There's a lot of development going on and tons of new features. There are so many features, in fact, that I put too much information in my slides, sort of on purpose, because I know a lot of people like looking at these things offline. And so I'm going to be trying to spend less time on those features that have been around a little while, but are still new to Solr 3.1, and more time on some of the newest features. So I have slides on most of these bullet points. I won't be going over them individually here. So there's a whole bunch of things, like I said, that are not in Solr 3.1 that I'm going to be going over, and they're currently only in the trunk version, Solr 4. Some of these might appear in a 3x release if they get backported. There have been a ton of recent Lucene performance enhancements. A lot of them I'm not going to go over here. Things like the flexible indexing that Uwe went over, that moved everything to bytes instead of double wide chars. The automaton query that made things like fuzzy queries 100 times faster, wildcard queries faster, regex queries faster. Really great stuff. But there's just no time to cover it all, so I'm just going to cover a couple relatively new things in Lucene land. The first being tiered merge policy, which is now the default. So how Lucene always used to work in the past is that you'd be adding documents to an index writer, and as you added documents to the index writer, it'd be buffering sort of the index state in memory until it was time to flush it out as a new segment. And Lucene would go along and it would flush out 10 segments, all roughly the same size, and then it would merge it all into one big segment 10 times as big, because the merge factor is 10. And so it'd keep going along until it got 10 of these big segments, and it would merge it into another segment 10 times as big as that. So it's like logarithmic, like a number system. So now how this new this new policy works is called tiered merge policy. Different from the old one is that it's not always just merging adjacent segments. It can merge non-adjacent segments to get a better merge. And it can select something other than 10 segments to merge too. It can decide that, oh, if I just take these 5 segments or these 7 segments, that's a much lower cost merge. One effect that has is that some people might have code out there that depends on doc ID order. The fact that the merge policy can now select non-adjacent segments might mean that that code no longer works. So for example, the code that if they add one document and then add another document, always depend that this internal Lucene doc ID is always going to come before this other Lucene doc ID. That code is now broken. So you can either try to rewrite it, or you can go back and use the older log merge policy. One of the greatest features of this new policy is that it doesn't over-merge. You could get into situations with the older log merge policies where you just add a single doc and you set off this cascade of merges. So, it's like, oh, that just happened to flush this segment, and that just happened to merge this lowest tier, and that just happened to cause a merge on the bigger tier, until you get an optimized index. And you're like, well, if I had wanted an optimized index, I would have called optimize. So That no longer happens with this new merge policy. The next thing I just want to touch on briefly, because it's cool stuff. It's all under the covers though, just performance enhancements, so you don't really have to do anything specific to take advantage of it. You just sort of get it for free. Is the new FST-based terms index. A finite state transducer is really just like a finite state automata, except instead of just matching an input sequence, it can also have an output. And so we have a new terms-based dictionary based on this. The old Lucene terms index was really pretty simple. It just had every 128th term from the index, from the term index, from the term dictionary, and that consisted of the term index. And so Lucene would just do a binary search across that, find the closest term, and then just iterate down until it found the term it was actually looking for. So this new FST-based index is much, much smaller in memory, so you can actually fit more information, and it's also faster to look up terms. And this picture is really just taken from the JIRA issue that started it all off. It's just an FST that maps a bunch of terms to their ordinal values. Document writer per thread is a very, very new addition that was just committed a few weeks ago, I believe. And so how indexing used to work in Lucene before this is that it was in parallel. So if you have multiple threads all adding documents, or if you're using Solr, multiple connections, the indexing of those documents was parallel in memory. And so all these different threads are building up thread states, essentially, until you detect that, oh, we have too much RAM buffered. And then what would happen is that a stop-the-world approach was employed. All the indexing threads were paused as all this information was merged and a single segment was flushed out. And so if you looked at the ingest rate over time, you'd have all these adds going on, really fast ingest rate, and then boom, it would fall off a cliff while the flushing was going on. And depending on how fast your I/O system is, that could be a while. And then it would go back up to really fast ingest rate, and then boom, fall down again. And so it didn't take didn't make the best use of resources. And so this is now changed with document writer per thread. So it happens just as before. All the stuff gets built up in memory. But when we detect that we need to flush something, only the largest DWPT is swapped out, a new one's created, and then that's flushed concurrently as a new segment, while documents can still be added and indexed in the other DWPTs. So the results were pretty fantastic. There's a committer who runs a lot of performance tests on the machine he calls Beast. It's like 24 virtual core machine, like 12 physical cores, I believe, and a really fast SSD. And I believe he saw like indexing speed up when he raised the number of threads to 20 of 265% or something on that order. So really, really great results. If you're using Solr, how you can take advantage of this is just use multiple indexing threads from your client, that basically multiple connections. Or you can use something like from SolarJ, you can use a streaming update Solr server where you can just configure it with the number of connections to use when talking to Solr. And that works really well if you have like just a single threaded document producer, but you still want to utilize multiple threads. Solr Cloud is something still relatively new. It was committed at the end of last year, but it's still a work in progress, really. And it's really our attempt to make the management of big Solr clusters easier. And so we've integrated Zookeeper, and Zookeeper is really a distributed system coordinator. And a Zookeeper quorum consists of multiple Zookeeper nodes for high availability and failover. So in our Zookeeper, we have 5 Zookeeper nodes here, so if 2 of them go down, the whole Zookeeper system can keep running as a whole. And it sort of exports a file system type API. And so the things that we store in Zookeeper is metadata about the cluster as a whole. It's really not for storing big files. It can really only take small files. And so the first section that we store is the config section. And that's basically what you would normally see in your conf directory of your Solr home. All that's sort of like uploaded into Zookeeper where the whole cluster can refer to it. So now you don't have to copy it around to all the different nodes. We also have a live node session that just it keeps track of what nodes are up. And then we also have a collections section that lists out the collections in our cluster. And so in this example, we have collection 1, and it has data that points to what configuration it uses. So what schema, what Solr config. And then under collections, we have the shards in that collection. So in this example, we have 2 shards, just 2 pieces of the index, but each shard has multiple copies for high availability and failover. And so under each shard, we have the actual physical locations of those replicas. So as a result of all this information being available through Zookeeper, basically every Solr server in the cluster knows what the complete cluster looks like. And so now we can do things like just send in a URL or request via URL to any of the Solr servers and just add distrib equals true, and then Solr will know how to look at all the shards and do a whole distributed search across the whole thing. And this is also load balanced, and so Solr knows that it needs to get the information from shard 2, and it'll make a load balance request to shard 2. So if one replica is down, then it'll go talk to the other. So this is really just a way, the simplest single server Solr cloud enabled Solr server, just so you can see what's going on. So the -zk run, that just tells you, run an internal Zookeeper server, so you don't have to go set up this Zookeeper quorum. And the top 2 options you only have to do once, and that just says take my local Solr conf directory and shove it into Zookeeper and sort of make me a new template, a new cluster template. And then you can go to the URL at the bottom, which is just a really simple Zookeeper browser that I wrote that'll let you see all the metadata that we're storing in Zookeeper. So there's a number of types of distributed requests we can make. The original way to do distributed search is you would give the complete list of all the shards that you had to hit to make up the request. But if you had shard replicas, you'd have to put those behind a virtual IP through a load balancer and stuff like that. So now Solr can do the load balancing itself, and you can give lists of equivalent servers basically by separating them with a pipe character. And so then if a request to one fails, then it'll go to the other one. Solr tries to be smart about its load balancing too. A single distributed request can have multiple phases, but Solr will try to talk to the same physical server for different phases of the same distributed request. And so that increases performance and consistency. Now we can also just specify which logical shards, which logical pieces of the index we want to query. So we can say, oh, just query shard 1, just query shard 2, or if we've separated our index, we've split it up by geographic region. In this example, we can say, oh, just query the New York shard, the New Jersey shard. That's all I'm interested in. In the next example, we already went over, you can just add distrib equals true, and that searches across the whole collection, so you don't even have to know what shards it's made up of. And it knows what collection to search because you sent it to, it's in the URL, collection 1. So it's all good that now you can talk to any Solr server in the cluster and get this distributed search going. But what if you don't even know the list of what servers are in the cluster? Well, you can even sort of delegate that to another Solr piece, a Solr J client called Cloud Solr Server that you just point at Zookeeper, and then it will slurp in the cluster state and do load balancing across all the servers for that initial request. Extended dismax parser, I actually said a little bit about that in the other session, so I'll skip over it, even faster now. It's supposed to be a superset of dismax. Hopefully it will end up replacing dismax eventually. It has full Lucene syntax support. Enhanced term proximity boosting, where it does the term bigrams into phrases instead of one big sloppy phrase query like dismax did. And optional enhanced stop word handling too, where it can include stop words in some parts of the query and exclude them in other parts. So we also have some faceting performance improvements. For facet.method equals enum, that's the method that steps over every term and calculates the set intersection with the base query to get the count. That initial population of the filter cache is now much, much faster, depending on how many unique terms are in that field. And I measured doing actually trying to facet on the ID field, something that you wouldn't normally do, but and measured up to a 32 times performance improvement for that initial field cache population. That also opens up some more uses for that method, the enum method, especially if you use it with the min_df parameter. The min_df parameter, you can sort of set a point where if a term is small enough that it matches fewer documents than that, it won't use the filter cache. It'll just do it directly off of the Lucene index. And only if it's above that point will it go to the filter cache and try to get the big docset entry to do the intersection. And so now that's faster too, and it can really save, so you can use the enum method in conjunction with min_df to sort of avoid blowing up your filter cache a lot. There's another couple edge cases that we optimized when we do really deep paging in the facets, like you want to start at page 1000 for some reason. That's probably not applicable to most of you, but it's there if it does. There's less memory consumed in trunk by the field cache entries, of course, because instead of having this big array of strings for the values, it's now a packed byte array. And so we got rid of both all the double wide chars, and it gets rid of all the object overhead for each value. Yeah, so we also have a facet.method equals FCS, a new faceting method that works per segment. The normal field cache method works by populating a field cache entry at the top level of the index. So what that means is even if you add another little segment to the index, the field cache entry will completely get rebuilt. That makes for really fast faceting, but slower turnaround time the first time you facet on that field after you reopen a reader or after you commit, essentially. So the per segment faceting works like sorting and function queries do. It's now on a per segment basis. Unfortunately, it's introduced a cost of merging the counts across different segments. So for most people, it's going to be slower. It's only going to be faster if you commit multiple times a second. And it only works for single valued fields currently too. We've added pivot faceting. This is really simple. I mean, it's really you give a list of fields and it facets on the first field, finds the top constraints, and then for each of those constraints, it goes and applies the constraint and then does faceting on the next field. And so it's sort of like nested faceting. And that's just a quick example of it, and you facet.pivot and then you just give the list of fields. We've added range faceting in 3.1. It's very much like date faceting, but it applies to all numerics now. And so you can just give a start and an end and a gap, and Solr will calculate all the ranges for you. It's just a nice, it makes things easier to use. You could actually do it yourself before just by doing a whole bunch of facet.queries and giving each range yourself, but this is much more compact. And spatial search, it's a very popular feature that was added in Solr 3.1. So it's pretty easy to use. You just have to index some documents with some spatial location in it first. So in this case, it's Just the store field is where the store is, latitude, comma, longitude. And then we have a bunch of spatial functions. And these spatial functions look at a lot of these global request parameters by default. You can actually specify these request parameters right in the functions themselves or the queries themselves, but it's nice if you're going to be using multiple of them in a request to just specify it once. So we have PT, which is our point that we're searching in reference to. We have D, which is the distance that we're interested in kilometers. And we have S field, which specifies the name of the field that contains the spatial information that we're comparing against. So the first type of query we have is like a spatial filter. It's normally used like as a FQ, a filter query. And it's just, we just say geofilt. And that gives us everything within the blue circle, within 1 kilometer. We can also specify a bounding box. That's if you just want a box that contains the circle. You might be interested in that. It's a little bit faster than geofilt because it doesn't actually have to calculate the distance of any individual points. And you may not need that type of accuracy, especially if you're going to be sorting by distance also. And then we have our distance function, geodist, which actually calculates distance. You can now sort by any arbitrary function query. And so we can also sort by distance ascending to get things that are closest first. But the fact that we did geodist as a function query is really cool because you can use it anywhere you can use any other function query now. So you can do things like sorting by, you can do things like combining the relevancy score of the query with the distance. And maybe you'd probably want to do it by inverse distance. So that's all in 3.1. This last bit, returning the distance, we don't have in 3.1, but we do in trunk. And it's called pseudo fields. And so basically, we just like you can list stored fields in the FL parameter, field list, we can now list functions too, arbitrary functions. And so we can just say, yeah, return the geodist along with my stored fields for each document. So it's the final missing piece, really. And so that just leads into pseudo fields. And you can see you can just like include them right in with the other names of fields. And what comes back, by default, it'll actually use the function itself as the label for the value. We also implemented field name globs, which people have long wanted. That's just a nice little thing to use, especially in conjunction with dynamic fields. You may not know the exact name of all the fields you want to return, but you may know a pattern, so you can specify patterns of field names to return now. Another thing we changed is that you can specify multiple FL parameters. That's sort of functionally equivalent, but depending on your application, it may be a lot easier for you to say, oh, I just want to add this one thing and not have to go modify an existing FL parameter. Now you can just add another FL parameter and you'll get it all back together. We added aliasing primarily because having as labels these big functions isn't so nice sometimes. So you can just do like the alias colon and then the original value, and that works with anything. So in this example, we have a normal loc field and we rename it location in the result. And then we have our geodist and we rename it underscore dist underscore. Using underscores like that isn't mandatory, it's just a convention. But I think it might be a good convention just to avoid clashes with, name clashes with stored fields. And to just give a hint that you're like, yeah, this is a produced value, not a stored field value. And there's a lot of stuff still in the works that will use pseudo fields too. Some of it's like partially done and I think just needs tests and some other tweaks, but like inline highlighting. So, currently we have, you get a list of documents back, and then if you ask for highlighting, you get a highlighting section below that, and you have to correlate them yourself by the document ID. So using pseudo fields for this will just put the highlighting information right with the documents itself. So it just makes your life a little bit easier. And the same for explain for debugging. And I think we have planned the ability to retrieve the sort values too, and also the group value. One of the newer things in group by queries is you can return a flattened list that looks like an old style request. But the problem with the flattened list in grouping is that you can't tell what document was part of what group unless it was a stored field, the group value or something. So we can use pseudo fields to add in that group value. That's not done, but it's on the roadmap. So result grouping and field collapsing are really the same thing, two slightly different use cases, but really the same feature. It's about limiting the number of results per category. And we normally define category as the unique values in a field, a single valued field currently. So this is just an example of Google collapsing by site and limiting the number of results per site to 2. And this is an example from Best Buy of field collapsing. And they're just, or rather result grouping is a better description of this one. And they're showing the top 3 results per category. So TV and video is one category and movies is another category. And so in Solr result grouping, you can specify 2 different sorts. You can specify how documents in the same group should be sorted with respect to each other. And you can also specify how groups should sort relative to each other. It's also worth pointing out the facet counts on the left are unchanged by the grouping. So you may only be showing the top 3, but you're still getting facet counts across all the results. And that's exactly the way that Solr currently works. For different use cases, sometimes people want it to work the other way, and that's still currently a work in progress. So this is just an example of group by field. We also have group by query, which is exactly the same as like a facet.query, but instead of giving you the number of documents that match a query, it gives you the top documents that match a query. So here's all the grouping params. I'm not going to go over all these now, but the bottom 2 are the 2 new ones that present this flattened list back and can make it look like a normal non-grouped response. That can really save you time and make it easy if you're using like an older client that doesn't understand the grouped format. So pseudo join is something that's very new. I think it was committed just like a few weeks ago. And so basically, it's pretty, the implementation is pretty basic at this point. You really want to think of it as mapping one set of IDs to another set of IDs. There's no relevancy scores carried over. There's no information about which documents originally matched carried over. So it's really just useful for filtering right now. So in our example, we have blogs and we have posts. And the posts refer to the blogs by the blog ID field. And so the blog ID field contains the ID of the blog. And so if we want to restrict blogs, if we want to restrict 2 blogs that mention Netflix, basically it's easiest to look at these joins and read them right to left to figure them out. So we search for Netflix and we find it in a post, and then we follow from blog ID to ID. And so we get documents of type blog, essentially. So if we now employed faceting or something like that, we'd now be getting numbers of blogs. And the top documents would be blogs also. We would not get any posts. So here's some other examples. This first one goes the other direction, saying only show posts from blogs started after 2010. So again, we go right to left. We do our date query on the blog type object, and we follow from ID to blog ID, and that gets us to post objects. And then we apply that filter to our main query. Now the second example, I'm pretending to be like an intelligence agent or something, and I want to search for posts that mention Obama. And if I find one, I want to search all the other posts in that blog for bomb. And so this is an example of a self-join. So I do my search for Obama, but then I join from blog ID to blog ID, the exact same field. And so basically, you know, I find a post, and then I basically select all other posts with that same blog ID. And then the last example is an example of how you can actually nest joins. And it sort of assumes that now we have these other type of documents out there, website documents, and those website documents have a website owner field on them. And so again, we read right to left, we search for Obama, we go from blog ID to get to the blog objects, and then we map from owner to website owner to get to the website objects. And so then we apply that whole filter to our main query of BOM. We've also implemented a cross-core join. And so what that means is that, you know, where our query is first executed can actually be on a different core than the two, as long as they're still in the single Solr server in a multi-core system. And we just do that with, by adding from index, and then you give the core name of the from core. And you might want to do this for a variety of reasons, such as if you have one core that like updates really rapidly, but you didn't want to like commit rapidly on this other core because it would flush your filter caches or whatever. So pseudo join and grouping are sort of related. And so I thought I'd just, you know, put up a table on like how they're actually different and when you use one over the other. First note about the actual implementation of pseudo join. It's currently big O of the number of terms in the join field. That means it's not going to be fast for something like unique IDs at this point. This is really just the first implementation. We can definitely do fast implementations, but this first implementation is only going to be fast if the number of terms, unique terms, is low. It'll still scale well to a large number of documents, just not well to a large number of unique terms. It can take single or multi-valued fields, though, unlike result grouping. And of course, it's really only for filters. If you want like the top 3 posts by relevance for each blog, you really want to use result grouping. It's currently chainable. You can, just because it's a query, you can naturally feed the output of one into the input of the next. Result grouping is currently not. It's you can't like group by multiple fields at once, but people are looking into it, so it's not going to last forever. And pseudo join sort of naturally changes your facet results. It's a great thing to look at if you want to facet different ways and get different units. It's like sometimes you want your facet results in numbers of websites, sometimes you want numbers of blogs, sometimes you want numbers of posts. Then, you know, pseudo join is a natural fit there. Whereas currently result grouping does not affect your facet counts at all. It's just showing the top documents, but the complete set of documents that match the base query is what's used to generate the facet counts. And just another couple random things. We have an auto-suggest component. This basically, auto-suggest is like, you know, the user starts typing something and you want to show them auto-completion suggestions. And so we have a couple implementations now. The first, which was a TST implementation, is a compact memory-based tree. And the second is an FST-based implementation. And in comparison, it's slower to build, but it is much, much smaller and also has faster lookups. And it's really built off of the spell check component. So in all these cases, whether it's spell check or whether it's this auto-suggest, you get the same looking results back. So it makes parsing a little bit easier. We can now index with JSON. This format that I'm using here is actually not 3.1, but is on trunk in 3.2. It's a slightly simplified form where you can have an array of just JSON objects instead of having like the add tag and stuff like that in there. Pretty self-explanatory. We can also now get query results back in CSV. I believe this is in 3.1 also, and not just trunk. And it's completely round-trippable with the CSV loader. And the results are streamed back. We don't try to build it all up in the memory, so you can really point at your whole big index and say, give me the whole thing back, stream it all back to me, and for backups or whatever, or for input into another system, and it all just works. And last but not least, an update of, I think Eric Hatcher called it Solaritas. It's basically a velocity templating-based demo GUI. It shows off some of Solr's features. It's hooked into Google Maps. It just shows all the different type of facets you can do. If you click on another link at the top, it'll let you do a spatial search and limit your results based on where you are and a radius and stuff like that. All right, questions?
So how performant is join? So for example, if you have an index of 10 million documents and the child document set is maybe 1 million or 2, would that work, or is that going to just grind?
What part was 1 million or 2?
When you do a join, you first select the children's set, and then you look for documents that match that, don't you? Correct?
Right.
Yeah, so that set, if you start by finding, say, a couple of million, and then you want to find documents that match those.
That will be relatively fast. Like I say, I think it's going to be relatively scalable from the number of documents point of view. It's really the number of terms in the fields that we're looking over, because this is, it's really, think of it like facet.method equals enum. It steps over the terms in the 2 fields until it finds a match. Well, it steps over the terms in 1 field, checks to see if it gets any hits in its base set, and then maps it, and then sees if there's a match in the other field, and then adds all those documents to the resulting set. So it's really, the bottleneck is going to be more that moving over all the terms.
For spatial search, does every document have a single point of interest, or can or someday will documents be able to have either multiple points or even better polygons?
Right. In the current implementation, a field can only have 1 point. It's called lat-lon field is the type, and it can only have a single point. It's basically because we use 2 underlying fields under that, something called polyfield, and so it indexes it as a latitude and a longitude. So if we allowed it to be multi-value, we'd really get latitudes mixed up with longitudes and could mismatch them and stuff, and so that's why it's single-valued for now. That is being worked on. There we go. There's a spatial guy right over there, Ryan. So I couldn't see you there, Ryan. I've got this light in my face.
You said that the building time of the 3-state transducers were faster than the finite-state transducers. Are there any circumstances under whether finite-state transducers are faster? We were told by David Wise that it would be linear if you had sorted input. Are there any assumptions about the data?
Is this for the suggester or for the terms index?
Well, I guess it would be for the terms index.
I don't think so. I don't think it should be. There should be cases where it could slower, but I bet there must be some kind of corner case, but it's certainly never going to be on average. Just because the old way of doing it, of just picking every 128th term, just really wasn't great, especially when you have all this stuff mixed together, like numerics and text. And so it was just like really non-optimal, and so like FST was just much more optimal. But yeah, I'm not really the expert on that area.
Thank you.
All right, great. Thanks everybody.